some interesting people if you get involved with the CS department. And I and others would be happy to work with you on that. So please talk to me if you're interested in doing that. The TAs are an important part of the class. So I'd like to continue our conversation. The idea is to give you a little experience in algorithm design using our tools, and we're using robotics and computational geometry as an example of how we might approach that. And with that having been said, I want to go over to the document camera, share my screen, and we'll do a little bit of stuff on paper, picking up where we were before. So I'll let you absorb that while I move over. So if this is working, you should be able to both see me and see the paper on the document camera. Is that working for you all?
Yep.
Yeah.
Good. Glad to hear it. Okay. Now, we wanted to get into algorithm design a little bit. And we talked some last time about circular lists. And today I'm going to do some other topics. I'm going to convexity and amortized complexity, a little bit of lower bounds. These are important topics you'll see more into 3:30. Give you a little tour of what lies ahead for you in computer science, but also useful tools in your daily lives. So remember, we were interested in having natural representations, on the computer, so to speak, of physical and geometric objects, such as polygons, which could be maps or CAD/CAM models. So with this idea that a polygon, in this case with 5 vertices called B over here, could be represented by a list of 5 pairs of rational coordinates. And we talked some about how we could represent such a thing using singly linked lists and doubly linked lists, how they are naturally implemented in Scheme, how doubly linked lists could be implemented with a memory model. And then we introduced the notion that these could in fact be circular lists, either singly or doubly linked lists, because of course, in some sense, a polygon doesn't have an end. So it's unnatural when you fall off the end with a null coulter. Why should it have an end? Why shouldn't it go around forever? So every point has a next and a previous. And we could implement that with circular lists using mutations, that is, setter functions in mutable lists. And this led to a fairly natural notion. However, we discovered that some of the functions that we know and love might not behave very well on circular lists. They might never stop. And these would include length and copy and map and various other nice functions like this that would never terminate. They just keep going all around. So it raised the question that to make such things safe, i.e. they will terminate, could we write a predicate called circular, or we tried circular try here. And what could that do? Well, it could test whether a link was circular by following the pointers. And with your collaboration, we did a very good job on that, in my opinion, and someone from the class was able to say, well, if you had a circular list like this, you could clearly detect circular list in linear time and constant space by simply keeping a pointer to the first point in the list that it loops back to. If it loops back to, you test it. You test every point you visit. Is it the first? Otherwise, you fall off the end with a null coulter. So that's a very efficient algorithm, in fact, an optimal algorithm. However, there are different kinds of circularities, such as the so-called row list, the Greek letter rho, pronounced row like this, not Ensign Row from Star Trek, but row like the Greek letter. And you see that a circular list like this, that algorithm will fail because it will compare every node to the first node. But in some sense, we have to do something more clever to detect these things. And let me guarantee you that if you have a so-called row list like this, which is easy to make, in fact, we made some last time, that functions like length and copy and map will clearly run forever on these things because they can't detect it. So how could we have a thing better than circular try that would work in this case? And let me just remind you of kind of how these things played out when we talked about them. We had something that looked like this for circular try, and you can see it here. What it did is it tried to say, just keep track of the first thing you began with, compare everything else to it as you cutter down the list. And when you're done, you either fall off the list or you counter begin again, which is fine. But we encountered when we produced a row list that even circular try would run forever. So I posed the question, can you devise a faster algorithm? And or decent algorithm. And we came up with some initially. So for example, we came up with an algorithm that was linear space and n squared time. And then I sketched how we could improve that using binary trees, because in binary trees or log query structures, you can insert and delete from a binary tree that's balanced. in logarithmic time. And so therefore we could come up with a little bit of work, a linear space algorithm, order n, and an n log n time algorithm for testing these lists. But I posed to you last time, and I'd like to loop back with you, does there exist a faster algorithm, namely something like circular trie, but runs in constant space, order 1 space, and order n time for circular lists that could be row lists? So I'd like to start off after that recap of asking you all, how did you do on this? What's your idea? How could we come up with such an algorithm? How would it work? So please tell me what you think and whether you have ideas on how to do this. What do you think? Does anyone have any ideas?
Just a quick question. From last time, the best that we got was n log n time and O of n squared space.
Actually, order n space.
Order n. Okay.
That's correct. That's right. But I claim this is an easier problem than some of you have done in the past, because I'm not asking you whether it exists, I'm saying it does, and can we engineer it? Although it's certainly not easy. Can we do it in constant space, order 1 space, and can we do it in order n time? So how would we do such a thing? So while you think about it, I'll tell you a little story about this, about how this problem has evolved. So, this is a fairly ratio-shaped problem. At one time, it was really only of interest to theoretical computer scientists like myself, mathematicians, came up every now and then. And it turned out to be extremely important in the area of garbage collection, which of course languages like Java and Scheme have to recycle things you don't need anymore. So it turned out to be important in systems after a while, but still was known either as a mathematical trick or systems trick. But when it started being taught in this class and others, it kind of got out there because so many people know about it who are working in industry. And as an anecdote, my daughter is in college and her girlfriend is a computer scientist and interviewed for internships this last summer. And at 5 out of the 6 interviews, she was actually asked this question, which fortunately she knew, having sat around the dinner table with me and others at one point. All right, a question from Cynthia. Yeah, so Cynthia asked, can you keep track of the visited addresses? So this is a clever idea, but it requires more space. So you can keep track of a constant number, but you can't keep track of them all. So clearly that would be another space, even if you only had 1 bit or a small number of bits, that would still be a linear amount of space to keep track of them all. So I want to say that's not what we want. And also, I don't want a solution that has side effects. I don't want to mark things. Another question.
Yeah, I had a question about n in this scenario. So what exactly does n mean? Does it mean like the number of nodes in the list?
Yes. Yes.
Okay.
Yes. Number of circles in this case.
Okay.
Yep.
Because I just wasn't sure how you calculate it because it's a looping list. So like length doesn't really have a strict meaning in this scenario, but okay.
Well, it does actually.
Oh.
Just the length function doesn't work. It's the number of nodes,
Okay.
right?
Okay, fair enough.
Yeah, think of it as a graph, which you're familiar with. Perfectly reasonable question. I dispute that it's not well defined, but it's very reasonable to ask this question, but I think it is well defined at this point. So think of a graph with cycles has a fixed number of nodes. We don't say that's undefined. So any ideas about how to do it? Here's the question. So I think Rachel has a pretty good suggestion. And let me try to flesh that out briefly for you. And Rachel, if I'm not describing your idea correctly, please jump in and tell me if I'm expressing your idea in the right way, or if you have any things you'd like to say that would make it clearer. Okay, so yeah, so Tommy, you have a good solution in the chat, but it requires linear space. So, or probably logarithmic space, if you count correctly. So it's certainly a good idea, but I think it will require more space than I want to use for this, just because I can't. So great suggestions. You all are thinking the right way, you know, in a clever way about this. Let me try to flesh out Rachel's suggestion. So Rachel's suggestion, this is sometimes called the two-finger algorithm. It's confusing because there's another one related to merge sort. And often when I teach this or when someone comes up with it, I don't actually reveal it if no one can come up with it. So we're lucky that you all work so hard thinking about this. Often we do it at the board and we have two people with different fingers and so forth, but I can't really do that right now. So what I'm going to do is I'm going to start out with two pointers. And there's a fast pointer and a slow pointer, and the fast one will be red and the slow one will be blue. And at every step, what's going to happen is the red pointer will advance 2 nodes and the blue pointer will only advance 1. And if it's a circular list, then eventually the red pointer will catch up to the blue pointer. Otherwise, the red pointer will fall off the end of a list. So let's sort of animate that and see how it works. And I'm going to assume that I can detect when I fall on top of another pointer. I'm also going to assume that I can detect when I skip over a pointer. That only gives you a constant factor speed up, but it's useful. So red pointer, the fast pointer, blue pointer, the slow pointer. I would do this with fingers, but my fingers are too fat. So that's why it's called the two-finger algorithm. All right. Invented by David Moon, the inventor of the Lisp machine. Right, interesting. All right, so here are my 2 pointers. They start out here, right? And let's just do it. Remember, red pointer, 2 at a time. 1, 2, 1. That's one step. 1, 2, 1. 1, 2, 1. 1, 2, 1. 1, 2, 1. 1, 2, and I've caught the blue pointer. So we've detected, because I check it each time, so I've detected that this is a circular list. So this obviously only takes constant space because I only need 2 pointers. And to prove that it runs in linear time is actually an interesting exercise. It doesn't run in exactly n time. It depends on how many times you might have to go around this loop. That relates to the GCD of this length here and the length of the loop. And you know about GCD from our previous work. Now, of course, writing something down as a an animation of an algorithm is only an idea. And so I've also written the code for you, which you can look at, but I'm probably not going to go through it right now. So the two-finger algorithm, of course, is beautifully implemented in Scheme, like most algorithms. So here's the answer in Scheme. And you could see it has the same bones here. So we have a helper procedure called the two-finger algorithm, and we initialize that by just starting off in slightly different places. So +1 and +2, +1 and +2. The 2 fingers go around. The main thing here is that we could her down just once on finger 1, twice on finger 2. This corresponds to incrementing once. This corresponds to incrementing twice. We also check for falling off the end of the list. So very nicely done. Linear space, and linear time and constant space. Rachel, was that what you had in mind in your suggestion? Good job. Okay, so very nice. Very nice work. All right, so we've solved that problem. And that's optimal. You can't do better than that. And we'll talk about how we know that. Yes?
Is there any reason you use the mutable lists as opposed to non-mutable lists using mcdr?
If I don't do that, okay, yes, there is. Can you think what it is?
So I guess the row list would have to be implemented in it as a mutable list, but I was sort of questioning why F2 and F1 would have to be implemented as mutable, I guess, pointers.
Oh, that's a great point. Well, a row list, first of all, a row list or a regular or circular list has to be implemented as a mutable list, right?
Right.
Yeah. So the thing is, I mean, F1 and F2 are just objects, right? But I can't remember the abstract. You're actually asking a great question. It's one that hasn't been asked before in this class, although it does come up in computer science. So excellent job. So the thing is, the abstraction is mcons, mcar, and mcooter. And you can't get at anything in an mcons without an mcar and an mcooter. You have no other way of getting it. You can't car it, it's the wrong type. You can't cooter it, it's the wrong type. Right? So this is the constructor, these are the accessors. So once you have a mutable list, you can't get at them any other way. Does that make sense?
Yeah.
Yeah, so try making a mcons and then carring or cooter it, you get a type error because car is only defined on non-mutable lists, the same for cooter. So great question, actually.
Okay.
Good, thank you for bringing that up. Rather deep question, actually, but we won't go more into it today, but I think that's a good answer. Great point. More questions? And by the way, this is at the heart of every garbage collector. It's in every system that can have circular data, which is, of course, every operating system. So this is, used frequently in architecture. And this is one intersection of our class with architecture and systems, is that every person working in systems knows this algorithm. They didn't drive it through mathematics maybe, but it's well used. Was there another question? All right. Okay, we can obviously take more questions and go on with that. Let's do some more with geometry and algorithms. So then we just have algorithm design. Yes, there is. So I want to make some comments as we talk more about polygons. So one of the things that will be crucial for what I do now is that a polygon is an ordered list of vertices. It's not an unordered list of vertices. So that's natural in scheme where you have orders. But if they're not ordered correctly, you get crazy things, and I don't want to deal with that. So for example, if we have this rectangle here represented by this list of vertices, and we think that represents this rectangle, they go in this order. Give them in the wrong order, you get crazy things that might look like this, or crazy things that might look like this. And I don't want to deal with them, and neither do you. So basically the point here is that only the first one of these is a rectangle. These are different orders of the same vertices. If you're solving one of these problems and you return the second one of these second two, it's wrong. Even though it's possible to compute the first one from the second one, you can prove that it requires more than linear work to do that. So the way we phrase this mathematically is a well-formed polygon has its vertices in cyclic order in the way it should be as a geometric shape. So we're not going to do those things. The order is a key point. And I mentioned this because otherwise we can definitely get into trouble. Okay, so let's develop some other algorithms based on things like polygons that we might see in robotics and we might see in geometry and machine vision. And to do this, I'm going to tell you a little bit about convexity, which you may have seen in a high school math class, or you may not have. Let me give you a general definition, then we'll specialize it to make it computable a little more useful. So if we have a set, say A, and it's just in real space, I don't really care about the dimensions, say Rn, we call it convex. If for all points X and Y in this set, the line segment XY is entirely contained within A. So this looks something like this. So let's take a convex set that's just in the plane here like this. Here's our polygon A like this. And it means that no matter what points we pick, X and Y, that are within A or on the boundary, the line segment XY is entirely contained within it. In contrast, if we have something like this, that's supposed to be a polygon. In this case, there are many points, line segments that are contained, but if we picked our points X and Y to be like this, X and Y, here's a line segment that is not entirely contained within A. So this is non-convex. Now, I want to talk about this definition, but let me mention that it follows from this, a corollary, that we can also just look at the angles if we're in the plane. It doesn't work in 3 dimensions as well. So if we're in the plane, it turns out that all of these internal angles are less than pi, i.e. 180, less than equal to pi, whereas here we have one that isn't. So we can say that a polygon, say B, which is in the plane, is convex if all internal angles are less than or equal to 180 degrees, or pi in radians, like it is here. So we have a definition here, and I want to talk to you about the interplay that we'll be seeing going back to lecture 1 between what is true mathematics, declarative knowledge, and how to compute it, imperative knowledge or algorithmic knowledge. So if I gave you this definition of convexity, which is math, you actually could go about doing some kind of test here. You could imagine constructing a stream of all line segments and trying to filter them by whether they were inside. I mean, that's actually possible to do, but extremely expensive. And so this is a mathematical definition's declarative knowledge. It's not necessarily the best way to compute it. You want to go from the declarative definition to something that can be operationalized in an imperative sense. This is something you can check. We have a 5-sided figure. We can compute 5 angles and compare them each to pi, see if they're less than equal to pi, and we're done. So we have a linear time algorithm for testing for convexity of polygons. So again, I want to just point out this is declarative knowledge. And this is in some sense closer, it's not all the way there, to imperative knowledge. To make this really imperative, you have to compute the angles, but clearly it's quite close there. And I think that at this point in the class, as both programmers and mathematicians, it would be trivial for you to take this and turn it into an actual algorithm. So I want to talk about that interplay a little bit as we develop some algorithms for things. So let me give you a problem and kind of ask how we would do this that relates to this. So here's sort of a problem that comes up repeatedly in computer graphics, robotics, computer vision, data science, and so forth, which is given a bunch of points, can we put a convex polygon around them? So given P, which is a set, finite discrete set of n points in the plane, we want to prove 2 things. I'll probably sketch it rather than prove it. 1, there exists a convex polygon containing all n points. And 2, you can compute it in order n time. And let's imagine what the points looked like here. A bunch of points in the plane. I'm just going to give them to you like that. And so how would we do that? Of course, 2 in some sense implies 1 if you can do it for all polygons. But how can we do it, and how can we do it this quickly? What are your ideas on this?
I guess the main thing would be you just need to find the most extreme points, because obviously if you bound the most extreme points, the internal points are going to be bounded by that.
Yeah, so I think that's an algorithm. And how fast can you find the extreme points?
ON, because you just have to look through them and compare with the max and min that you store. So I think that's ON with O1 complexity.
Sorry, it's order and time and constant space.
Oh yeah, sorry.
Yeah,
O and space. That's what I meant.
Yeah, absolutely. Yeah, so that's an algorithm, and it's correct. So what we do is we run through all the points, and we compute what I will call x min, x max, y min, and y max, so the extrema and the x and y dimensions. So those will be points like this. Here's some of your extrema here, right? Things like this. And we're just going to use those to compute a box. So basically we'll compute something that looks like this. Based on the extrema of these points, right? So here we've satisfied both x min and y max. And here we've satisfied x max, and here we satisfied y max. So we compute the extrema of these. Basically, we compute x max, x min, y max, and y min. And this gives us the coordinates of what's called an axis-aligned bounding box, one of the most useful objects used in computer graphics and robotics and vision. So this is pretty cool. We found a convex polygon. It's very simple. It happens to be simply a rectangle, and we can compute it in linear time given these points. So that's pretty neat. And it's optimal, which is really great. Now, one of the things you'll notice is I haven't said anything about how good this polygon is. Like you could imagine a case where, we wasted a lot of space, or we took up a lot of space we didn't need. So in some sense, it's natural to ask what's the smallest polygon that can do this, and how can we compute that creature? And that's what I'd like to take you through a little bit next time. So here's a very useful mathematical construction that's like this, but I'm computing not only a polygon, but in some sense the best polygon, in the sense the one that wastes the least amount of space. So here's the construction of that thing mathematically, then we'll do some ways of thinking about it. This has a special name in mathematics. It's called the convex hull. So given a set, say V, of points in the plane, the convex hull of V is the smallest convex polygon containing V. And it's written convex hull of V, at least in this class. So this is incredibly useful as a construct. It's useful in robotics, graphics, animation, vision, GIS, biology, physics, mathematics, UI design, optimization, engineering, all kinds of things like that. So I'll give you a simple example, and then I'll try to think about how we do it. Here's 4 points in the plane, 4 points here, and 1 in the middle. In some sense, it works. You kind of filter this out. If this is your set V, let's add 1 more to make it interesting. Down here, our convex hull will look like this. So not an extra point. And even works if there are extra points in the middle like this. And of course, let me just remind you, I won't say this every time, this must be a well-formed polygon. So the output of an algorithm to do this has to have the vertices in cyclic order. So I'm not interested in an unordered list of these 5 vertices. I'm interested in a list that's in the correct order. So it's actually a polygon. Think of it as I have a dumb graphics routine that's going to draw this or shade it or do something with it. It has to be in order. Okay. Now, let's talk about how you might compute such a thing. Now, this is declarative. Obviously, this is declarative definition, right? This is declarative about this is mathematics, right? And you could imagine doing something like enumerating all possible polygons with rational coordinates and picking the smallest one and having streams and things. Probably not the way to go about this. It's probably going to be a lot faster to do a direct algorithm with some nice data structures. But we need to go from knowledge about what is true, mathematics, to an algorithm. And that's really what algorithm design is all about, and what we're going to talk more about today, given our newfound skills in sets and algorithms. You probably wouldn't implement a thing like this directly. Now, why do we have any hope of implementing something like this quickly? Like, why is it reasonable to think that this should be quick? And we have our success before, like getting some polygon, as your colleague showed us. This was done doable in linear time. So maybe with a little more work, I don't know how much more work, we'll have to discover that, we could do not this problem, but this problem, get the optimal polygon. Maybe we could do that. So that this is an optimization problem in some sense. So how can we devote ourselves to this? And why is there any hope of being able to do this quickly? And what is our intuition about this? So I want to encourage you to think about the most efficient algorithm we can come up with. And to motivate you, I have a visual aid here. So this is George, the geometry sheep. And George has some push pins, and George is going to help us with this problem. So here I've taken some of George's pins and I put them down here like this onto cardboard, like this. All right. So we're doing pretty well here. We got these points. Let's add a couple more so you can see the process. I want to add some more points to this. And then I'm going to try to compute the convex hull. So let's put a point in here. Here we go. And we'll take another of George's pens here. And we will put one here too. All right, so what's the convex hull of these points? And why should we have any optimism that we can compute such a thing efficiently? Well, one of the intuitions as we cross the barrier between physical computation or physics and actual computational electronic computers, you can imagine physical or mechanical algorithms that are incredibly efficient. So, I have these points now in the plane, but one way that I can compute the convex hull is to take a rubber band and go like this. And you see the rubber band is optimizing for the minimal polygon because that's what physics does. And so in some sense, I have computed the convex hull of George's points here by merely stretching a rubber band around them like this. And I have computed this essentially very quickly. I'm not sure it's constant time, but it's pretty quick. I'm not sure that the amount of time to put the rubber band around this really took a lot more time than constant time. So you might hope that you could do such an operation extremely quickly. And as you can see, it has the right properties. It's the minimal polygon. We don't include these points in the middle. And of course, we could read them out in order, which is what we want to do. So you might hope for a very fast algorithm here. And so might George, the geometry sheep. Okay, so here's an example. I hope you enjoyed this demonstration. I usually threaten when I have a blackboard to drive nails into the blackboard and test the limits of the tenure system, but cooler heads in the student audience usually restrain me from doing that. So let's ask, how can we solve a problem like this? We want to find the minimal polygon, and we have some indication that it might be possible to do such a thing. So how could we go about thinking of a problem like this? So let's thank George for his endeavors here and let him go back to holding my push pins. We now know what a convex hull is, and that we've seen a demonstration by a plastic sheep. How many classes can you see that? So let me ask you now, how would you come up with an algorithm that would compute this optimal or smallest convex polygon? What would it look like? Thank you, Michaela. So go ahead.
Sorry, go ahead.
So I'm sorry, you go ahead.
I don't have a complete algorithm. I just have a bit of intuition. But it seems to me like you're trying to find extrema in a different sense, and here it's a sense where for your extreme points are ones where there's no point that is higher than it in both the x and y axis.
Yeah, I think you have a good intuition there. I think one thing that's complicated is I could have rotated this so it wasn't quite as axis aligned, and then it's not really clear what x and y mean in that case. It's kind of independent of axes, right?
Yeah, but I mean, if you're defining points along a like I don't see how else you'd like have it in a computer system where you're defining points. I feel like there has to be some sort of plane that it's aligned to, and if you have such a plane, you can essentially say, here are all the points where there's no point greater in both the x and y.
Yeah. By plane, did you actually mean line? Like, I would call this, the infinite line supporting this. Like they live in a plane, right? But would you
Right.
have called this? Well, it is of course in some sense a plane mathematically. But if I extended this to be infinite, would you call that? Is that what you're calling a plane?
Not really. I think the what I'm trying to essentially say is like if you have a bunch of points, right? You're trying to find all the points for which there's nothing up and to the up or to the right or down and to the left, if that makes sense. That just from like I don't know how you translate that into code, but that seems to be my intuition there.
I mean, I think it's a good intuition for the kind of thing you're looking at. Let's maybe run with that and see where we can get. So. And here's our ideas about how we could turn this into sort of the idea of an algorithm. So this is one, let me sort of riff on your idea a little bit, and maybe I'll ask you all the complexity of it, because this is, this I think could take a little while to, come up with something. So there's an algorithm, and we're going to try to get successively better ones. This is something called a gift wrapping algorithm. I think it embodies, there's several ways we could do it, kind of embodies your idea a little bit. So the idea is, suppose I'm given some points and I say they look like this, and I have a bunch over here like this. They're not in any particular order. I mean, they're not given to me in any order, right? So what a gift wrapping algorithm tries to do is sort of, I think, along the lines of what you're saying. I tried to, tune this to your suggestion. This is my set of points V, obviously, here. So what I'm first going to do is I'm going to find the point with maximal X value, which is this guy here. This guy. So, maximal X value there. And what I'm going to do at this point is I'm going to draw a vertical line. If I can draw vertically here, I think I have to rotate the paper a little bit. I'm going to draw a vertical line like this from that point. And kind of consistent with your idea then, for the rest of the points, all the rest of the points, I'm going to compute the slope to this original point here. So let's call this point here P1. So what I'll do for all the rest of the points is I'll compute a line like this, and I'll compute their slopes. Obviously, it won't be in order. I could have these guys here like this. And obviously, that takes linear time to do. And then I find the point with the minimal slope, right? Because I'm kind of wrapping this gift paper all around it. And the point with the minimal slope will be this point here, P2. And now I repeat the process, except that I rotate the paper so this one is up. So now I rotate so this one is straight up like that. And I now do this line like this. And then I have to take all the points and I have to sort them relative to this slope. And then I take the point with the next greatest slope. So remember, my convex hull has already started. I have this now. I pick the point with the next greatest slope like this. And I work my way around, and eventually I'll have a convex hull until I get back. So this will clearly work. I'll get something that looks like this in this case, because I'm always taking the one with the slope. And the idea of rotating the picture, so to speak, so the line I just drew is now the y-axis, I think that's similar to the idea that was proposed by your colleague about how to go about doing this. So in short, first find the point with the maximum x value, draw a vertical line from that point. For all the rest of the remaining points, compute the slope of the line P1 to that other point. Then find the point P2 with the minimal slope. That point will be on the convex hull, so add it there. And repeat for the set of points where I've deleted P1 and P2. Just keep doing that and use that next line as vertical. So a sketch of an algorithm. So let me ask a couple of questions here as we sort of think about this. This is, I think, kind of cool. So let me ask you to think for a minute, and I'll even turn myself off while you think. How would we go about computing the complexity of that algorithm or calculating it? What do you think? So take a look at that, and then I'll come back to you in a minute.
I actually had a question.
Absolutely. Let's look at your question.
So at the far left of this polygon, you have these 3 points where 2 of them appear to be vertical to each other, and then you have this middle point in the middle. Do you see what I'm talking about?
In here?
Yeah, right there. So it seems to me that you the GIF wrapping algorithm would tell you to go straight from the top to the bottom, but wouldn't it be more like less space if you went top, middle, bottom?
Well, I think it would all basically wash out. I think it would not be. In my opinion, it would. I think it would only change a constant factor, but I could be wrong, right? Could easily be wrong about that.
Okay.
Yeah, I mean, it's an interesting idea, but I think it's not an optimization that's going to change a lot, given that this algorithm. I guess I'm kind of giving things away, but that algorithm isn't super fast, really. That I gave. I mean, it's sort of okay, but it's not maybe the greatest algorithm in some sense. So I don't think it would make a huge difference. Was you worried that they have exactly the same coordinates? Or
No, my worry is more like according to the problem specification, you need to create the smallest possible polygon. Oh, okay. Would it okay not be convex? Okay, thank you.
Yeah. No, perfectly reasonable point. Very, very reasonable to think about. Okay. So I now see what your point was. I think it's good that we
Oh, okay, that makes sense. Yeah, okay.
Yeah, because it has to be convex. If it can't be convex, all sorts of pretty crazy things can happen.
Yeah. Okay,
Yeah.
thank you.
Well, so it wouldn't be a convex hull, but great thing to think about. So given that we have an algorithm that maybe we think is going to be correct, I mean, maybe, what do you think the complexity of this algorithm would be in terms of n? We'll say n is the size of v, right? So how do you think this would run? Just time complexity for now. What do you think this works out to?
O of n squared.
Yeah, I think it would be. Can you tell me why?
You have to check for you have to check through all of the other points, which is O of n, and then you repeat that n times.
Yeah, I mean, it goes down because you're deleting points. That's the one quibble I would have. Do you see that? Because I don't have to check all n points each time. I have to check first n, then n minus 1, then n minus 2. Does that make sense?
Yeah.
Yeah. So let me just rephrase your analysis. Tell me if I got anything wrong. So identifying this first point here, that takes linear time because I have to look at all the points to get the one with the extreme value there. And then if you think of the loop in some sense, when I'm checking all the other slopes, the first time it's n minus 1, right? Because I don't have to look at this one, but then I have to look at n minus 2 plus n minus 3 plus n minus 4, etc. And of course, this is the sum of I. This is equal to order n squared. So this is an order n squared algorithm, but still much better than an infinite stream. So that's pretty good. I mean, infinite streams can be very efficient, but it's not necessarily for this particular problem. All right. So we have an algorithm for this. Question.
Quick question. With that, so of course each step is going to be order n, but this.
No, that's not correct. Right. each step is not order n,
Well,
right? It goes down by 1 each time, right?
we're down by 1, but so this, but we
The
don't.
reason this is n squared is not that each step is order n. The reason is that the series I equals 1 to n minus 1 of I is equal to essentially n times n minus 1 over 2, right?
But why do we have, or like, why does the series go all the way through n? Like in this case, say only, because all these internal points we didn't have to do this for because we reached.
You don't know they're internal. How do you know they're internal?
Well, but once, so we start at P1, we go to P2, we go all around this loop, and then eventually.
Yes, at the very end, you're right, because you'll only have n minus 2 points around the loop. But think of it here, when you have just P1 and P2, we don't know a priori that these points are inside, right? You have to compute that.
Right, so I know that, but so we have to compute all of the n being all of the points that will end up being our loop, plus all of the internal points. But then at the, once we are almost finished with our loop, kind of the n minus 1th time, we'll compute on all of the remaining points. And we'll,
No, you won't. You won't. So basically at the first step, you have all the points minus P1, because that's your anchor. The second step, you have all the points minus P1, P2. At the third step, you have all the points minus P1, P2, P3, right? And so the first time you're looking at n minus 1 point, second time n minus 2, second time n minus 3. So you're not looking at the slopes, comparing the slopes of points that are already on the hull. You're just looking at the unassigned points so far. So in answer to your particular question, when you're all the way around the loop, say there are only 2 points left, then they're only, then basically you'll have n minus 2 is 2, right? Because look how this goes. Because you're not comparing to things you've already put on the hull.
I'm asking you about this later, but like what I'm thinking is that we at some point, we're going to keep going through this n minus 1, n minus 2, and n minus 3. Whenever we get to the step where the smallest slope is that original P1, we can then stop, and then we never we won't have to go through this process all the way down to n minus n, because all these internal points will never be kind of the current point, because we never have to consider them.
But by that time, we're all the way down to n minus n plus 1, right? We're down to 1. When you get back to the initial slope, I mean, the series automatically takes care of that. Like that will happen when you have all the other points, right?
I don't think so, but I'll talk. If you mind, I would like to talk.
I see. You're talking about the internal points. This is the size of the hull. Yeah, so I'm talking about worst case complexity.
Okay.
So let me explain.
Okay.
So in computational complexity theory, we're always interested in worst case complexity. The worst case complexity is every point's on the hull.
Okay,
right?
I understand.
And so that's the analysis I've done. But you have a very good point, which is there could be a faster algorithm than n squared, and it could exploit some of these ideas, but not exactly in this context, which is kind of an interesting way to think about it.
Cool. Of average.
Yeah.
Worst
Yeah.
case. Thank you.
Right. So we haven't seen tools for doing average case complexity in this class, and you will see them later. But I actually don't need average. I actually can do a little better deterministically, actually, and it uses some of the ideas you brought up. But I now do see the point you're saying, which is that it isn't a worst case scenario if you have lots of internal points, but it is difficult for algorithms without some sophistication to take advantage of that. So this brings us to the next way of thinking about it. Well, how can we do a little bit better in terms of the complexity? Like, how can we think about that? And maybe I can incorporate some of your ideas, which I apologize for not immediately understanding, but I do see your point. So let's see if we can come up with something that maybe is just a little bit faster, sketch how this might work. So one thing that you might consider in a problem like this is to do some kind of divide and conquer, right? And this is a classic paradigm, of course, in computer science. It also works very well here. So again, we have our V, which is our set of points. And what we might like to do is we might like to divide them in half and solve the subproblems. And so if we had some points that were like this, in a felicitous example, we can imagine computing the median in X of these points. And it turns out you can compute the median in order n time. You could also sort them by X value in n log n time, but let's just compute the median. If you can compute the median, then you can divide these points in half. And if you can divide them in half, then once you've divided them, you can solve the separate convex hulls that look like this. Right, we call ourselves recursively. We're going to get a recurrence here of some kind. And then I put them together, combine the two hulls into one bigger hull. And if I can do that, I'd have a recurrence that looked like this. Sorry, this equal sign. But I need some time to combine them. So how can I combine two nice convex hulls that are separated in this fashion? So I've given you a handout that talks about this in some geometric detail. But the basic idea is that you imagine finding the min and max y values of each of these hulls and sort of build bridges between them, or tangents. And the idea of doing this is I can really make any bridge between these. I mean, it's nice if you'd like to eventually make a bridge like this, right? That's what you really want to have happen here. But how do you get to that point? You can make the bridge by connecting any 2 points on the hull and then asking, can you raise that bridge by traversing the hull? And if you can raise it, i.e. increase the y value, then you'll be improving it. And eventually you'll reach a maximum because of convexity. So in order to be able to do this bridge finding algorithm, you clearly need to be able to traverse these polygons both forward and backwards. So the ideal data structure for this is a doubly linked list. And if you do this, you can actually merge these in linear time. So to merge them in linear time, once I found the two bridges, namely this bridge here and this bridge here, that are optimal in the sense that this bridge can't be raised anymore to the sky, this one can't be lowered anymore towards the floor, then I do surgery on the lists and I delete this portion of this hull and this portion of this hull, change the pointers and sew things back up together. And this recurrence turns out to reduce to roughly order n log n. So there's some details of how to raise these things. Let me point you to the right place in the notes if you want to look at it. As I mentioned, you build any bridge since you can traverse the polygon in either direction, up and down in constant time. You basically ask how far can you raise them in order to get these bridges in place. But the basic idea is that we have a merge operation to do this. That's an interesting way to kind of pose this problem. Now, one cute thing about this algorithm for convex hull, which is faster than n squared, is that it actually works in higher dimensions, like 3 dimensions, which comes up a lot in robotics. But one of the things is this is a somewhat powerful algorithm, involves a fancy data structure and some other things that we need here. And I want to ask you, now that you've seen that it can be done in order n log n time, do you think you could come up with a direct algorithm that works in the plane, won't work in 3D necessarily, that could solve this problem in n log n time and doesn't use this divide and conquer paradigm? Not that there's anything wrong with that, but is there a way to do that? So let me let you think about that for a minute and I'll come back to you. Of course, you can ask me questions. And think about whether you could come up with a different kind of algorithm, wasn't divide and conquer, but could run in n log n time. And let's try to see if we can get to that in the next few minutes of class. I'll give you a couple of minutes to think about that. Feel free to ask me any questions or ask each other any questions about this. So let's come back and talk about this a little bit. This is a favorite algorithm of theory people, algorithms people. And in some ways it's very powerful because it relies on this divide and conquer paradigm. But I found that at this stage of algorithm development, it's useful to see a solution that might run in n log n time that is kind of a little bit more direct, like a little bit more like the algorithms we've seen before. So I actually like this one a lot, but let's try to see if we can get any closer. Anyone have any ideas how we can approach this? This is a difficult problem, so don't feel bad if you don't.
I know binary trees usually run in log n time, so maybe a solution involving a binary tree somehow.
Yeah, you know, that's it's possible something there could work for sure. I think it's reasonable to look for things that have logs in them like that. I'm going to show you something slightly different, but I do think something could work out like that. So let's try to have something like this. This algorithm is by a guy called Graham. And it's often called Graham's scan. And again, it's like gift wrapping, but it's a little smarter in some sense. Maybe it's like your colleague suggested. So I'm going to assume I have a bunch of points here like this. Here's my points. Not given any order in particular. And I'm going to assume without loss of generality that the two-dimensional median is the origin. If not, in linear time, I can compute the median and I can just subtract off so that I have the XY origin being in the middle of this. So there's some origin here, which is this point here, say, and this origin, which I'll draw like that, is not one of the points, just the center of the XY coordinate system. So my first step, and this I think relates to the binary tree comment a little bit, is I'm going to sort these based on angle. So in other words, if I have a point, if one of these points is at coordinates xy, which of course xy are a pair of rational coordinates, what I'll do is I'll map xy to their angle theta, which is just equal to arctangent of x and y. So what I imagine doing here is placing a coordinate system at the origin of these things like this, right? X and y, like that. And for each of these points here, what I'm going to do is I'm going to say, well, it has some angle. Here's its angle. And that angle is theta. And I'm going to just sort these guys based on theta. So now they're all ordered around here, but of course they go in and out in some sense. Now, as before, I'm going to find the maximal x valued point in linear time, which will be this guy here. And then the basic idea of this is I'm going to traverse the points in V, my set, in theta order. And I'll remove dents as I do that. So what does that mean to remove dents in some sense? So let's look at a simple case here, kind of blown up. Suppose I start at a maximal point like this. And remember, my coordinate system is down here like this. So that's where the theta angles are. And I start traversing in this order, and I'm constructing an approximate convex hull like this. So far, so good, right? I have 3 points here in the convex hull, and then I have one in here like this. No problem yet, right? Right, I'm fine so far. But if I now add this point here, I have a problem because this angle here is non-convex. And so we'll call that a dent. And when I see a dent, I have to backtrack and remove it and repair the hull to look like this, and then I continue. So the algorithm can be thought of as find the maximal x point, traverse points in theta order, and remove dents. And obviously to remove dents, I need to have a doubly linked list so I can do this in an intelligent fashion. And so that in this case here, it would look a little more messy, but let's try it. It would look something like this. So what I would do is I would first have this point, say that's the second one. So my initial hull would look like this. Then I would come to this. I'd find it's non-convex. I'd remove the dent as follows. I would next move on to this point here. That's fine. Then I have this point here like that in order. Now I have this one. I come back here. That's a dent, so I remove it. Then I go around to this point here, to this point here, to that point there. That's a dent, so I'll remove it like that. And then I continue around the hull. So this looks pretty efficient, but how efficient is this dent removal? Like, it looks pretty bad. You know, obviously, if the dent is small like this, I could remove it and I could do surgery on the list in linear time. Why can I, in constant time? Why? Because basically I might have a list that looks something like this. And depending on how large my dent is, I can remove it quickly once I've detected it. So suppose I had a dent that's bigger than 1, I can remove it by just changing the pointers like this, using mutable pointers. The problem is, it looks like this dent removal will be a little bit expensive. So I can find the maximum x point in linear time. I can sort all these points in n log n time, which is nice. How quickly can I traverse and remove the dents? So this is kind of a possible problem for us that we have to consider. And I want to introduce you to the way that we can think about this. And you'll see a lot more of this in future classes. So there are only n points. And so the maximal size dent in the worst possible case is order n. And it would occur in a situation like this. Suppose I have started out at some maximal x point like this, and I have a bunch of nice points like this that are possibly on the convex hull. I could actually, in the worst case, put a linear number of points, almost linear number of points in here. Then I would come over to some point like this. And in order to add this to the hull, because this is non-convex, I would have to delete a linear number of points. So I have an order n size dent and order n size work to remove it. And then, of course, you can imagine continuing along the hull like this. You might have a point like this and a point like this. And our hull would look like this with a lot of points in the middle removed. So the problem with this approach, on the face of it, is that you could have a dent that was up to order n size. It can't be quite order n, but order n minus 2 or 3. And removing the dent could require linear time, because I have to detect the dent and remove these points. So that looks bad, because why couldn't it be the case that I have to remove a linear number of linear sized dents? But what you can see here is that in this particular case, we backtrack a linear number of points, but we only do this once for the points, then we delete them and never consider them again. And I think this relates to the comment we had earlier about internal points. So because once we remove these points, we never see them again, we do the work of removing the dents once, and it can't occur again. So in other words, the total work to remove dents is only linear time. And by working out the rest of this analysis, it's possible to show that actually the dominant time to do this is order n log n time. So removing dents can only take order n time. We don't know where the dents will be, but we know that when they happen, we charge them against our budget of possible points. And this is a branch of complexity theory that's sometimes called amortized analysis. In other words, I have a budget of n points. They can only form dents of up to size n distributed in some fashion. When I remove those dents, I remove those points from my list and don't consider them again. And so I can never encounter something that hard to remove in the future. So what I've been able to do is sketch really 2 different kinds of algorithms to suggest we could do this in order n log n time. Sketch a divide and conquer algorithm and a dent removal algorithm. Was there a question?
Yeah, sorry. So the n log n, does that just refer to like an efficient sorting algorithm sorting the points by theta order?
Exactly. That's exactly right. So we'd sort them by theta order. Then we traverse them. Obviously, traversing is linear time, but removing dents turns out only to take linear time. Because once we've removed a big dent, we don't see those points again. Okay. So when you think about what we've done here is we looked at convex hull, which was a math thing. And then we came up with an order n squared algorithm, which was based on gift wrapping. And then we came up with two different kinds of algorithms, divide and conquer, which were order n log n, based on a recurrence. And then we came up with gram scan, which is order n log n. And we needed different tools for this. Here we needed a recurrence and a little geometry. Here we needed very little geometry, but we needed to do this analysis that argues that the dents kind of don't add up. And of course, we get back a well-formed polygon. So as we move into the end of class, I want to make a couple of comments that are really advanced topics, although I will touch on one next Monday. So the first is that an advantage of the divide and conquer algorithm is it works in 2D and it works in 3D. And a lot of things happen in 3D, like the entire world and all of robotics and all of machine vision. Gram scan is very nice, but it only works in 2 dimensions, which is kind of an interesting point. So same complexity, but does not generalize to 3D. So I have 2 questions for you, one very advanced, which is, this divide and conquer algorithm is nice, and you can imagine computing convex hulls in higher dimensions than 3. In fact, I defined these sets to be in any dimension of real space. So one question is, will this algorithm work in 4 dimensions? And by the way, if you think that's bizarre, of course, 4 dimensions arrives in Minkowski space-time for physics all the time, but many data sets in data science, GIS, and financial analysis are 4-dimensional or higher. So it's interesting to ask if this algorithm can run and run efficiently in 4 dimensions. This is somewhat advanced topic, but I think it's worth pondering. The second question I'd like to ask you is the following. So we started out with a mathematical definition of convex hull, n squared to n log n. Are we done? Is it possible to do something even faster, namely linear? So the question is, does there exist an order n time algorithm or not? Now, George showed us a very fast algorithm using a rubber band. Maybe we could do something just fast like that. I don't know if we could, possibly. So the question to consider, and this is really different from computability, these things are eminently computable. I'd like you to think about, and I will address at the beginning of class on Monday, is whether it's possible to show that either n log n time is optimal, you can't ever do any better, or whether it's possible to come up with something even faster, namely a linear time algorithm, which would be the best you could do. How could we address this? How could we think about such a thing? And this is really a place that you'll go as you go on in algorithms, but also in industry, namely that when you're working on an algorithm, when are you done? Like here, we started out with something, we got n squared, that was too slow. We got 2 versions of n log n. One goes to 3D, yay. Does it go to 4D? We don't know. That's functionality, that's capability of the algorithm. But should we continue working it? Is it worth an additional 6 months effort to try to get this down to linear time? Or can we prove that there is no linear time algorithm and in fact n log n suffices? And these algorithms take a while to develop, even though they only take me a few minutes to tell you about. So I've described some of these algorithms in notes for you to look at. And I'd like to challenge you by thinking of this point here. Is n log n optimal, the fastest you can do? Or could we get down to linear time? How would you prove that either way? And I will discuss this further when we meet on Monday. And then I'll take some of these techniques and apply these ideas about polygons and convexity to some problems in robotics, which usually is a lot of fun. So in short, we were able to start out with some mathematical definitions based on whether things are convex or not, and come up with algorithms in the field of computational geometry to compute things like convex hulls and bounding boxes. By thinking about these more deeply, we could go from quadratic to n log n, and we raise this question here, which is sometimes called lower bounds. Is it possible for us to argue that n log n is optimal, the best we can do, or can we prove that there exists an order n algorithm? Equivalently, can we show there is no order n algorithm? So we have the same kind of branching that we do in computability theory, namely, is there an algorithm or not? That would be a great thing to be able to figure out. And we have the tools to be able to think about this now. So let's try to do that a little bit. And obviously very practical, because in a big system, say GIS or computer graphics, linear time versus n log n makes a pretty significant difference. And we'd like to know that, and then we can stop our efforts and optimize in other places. So the challenges are, and I realize there are many different people in this class, if you really like what I'll call somewhat higher mathematics, ask yourself whether the divide and conquer algorithm, which works in 2D and 3D, could work in 4 dimensions, and if so, what would be its complexity? If you like hardcore computer science, algorithm development, challenge yourself by thinking of this question here, which is n log n optimal for convex hull, or does there exist a linear time algorithm? I'm also happy to discuss this with you afterwards in the time we have after class. I'll stay here for a little while, happy to have discussions, or you can discuss on Piazza or via email if you'd like to do that before Monday. But we'll do this at the beginning of class a little bit on Monday. With that, I think that we are close to out of time. And so what I'd like to do is stop the recording. Thank you all for participating. You did a great job in working on these problems and in finding some very pretty cool solutions.